So in today's lecture, we are going to mainly talk about four things: vector space, subspaces, basis, and dimension. Fine. But before we start, let's do the DDP problem that I had given yesterday. So all of you, were you able to solve this? Maybe reply as a yes or a no on this. Anyways, I will solve. So yes, yes. Bharat, you were also able to solve, right? Cool. Anyways, I'll still solve this for the sake of completion. So what is this saying? So we have to check. So we have to check whether this set, which is given, x plus x square, 2x minus x square, is linearly independent, where x is a vector which is coming from Rn space. Fine. So how can we do this? So I am given a vector x, which is coming from Rn. I'm also given x plus x square, which is also a vector, and I'm also given 2x minus x square, right? So I can assume that these are three vectors, right? And then let me see what I do get when I add these two vectors, okay? So I am adding x plus x square plus 2x minus x square, right? So I can do this because I can take any linear combination of the vectors, and this is perfectly fine, right? To add these vectors like this. So what I'm left with is px, which is 3 of x, right? Or I can say 3 of b. 3 of b. 3 of b. Right? So what I'm getting is what I got, b plus c is equals to 3 of a, right? So these are, so b plus c is a multiple of a, or I can write b plus c is equals to a. So a is a linear combination of b and c. So because a is a linear combination, of b and c, the set is linearly dependent. Linearly dependent. Fine. Clear to everyone? Fine. Okay. So, so whenever you don't understand one thing, right, or anything, you can always unmute yourself and say no, that I did not understand. I will otherwise assume that everybody has understood. Right? Cool. So moving on agenda for today. So today we are going to cover these four things. So we'll talk about vector spaces, subspaces, basis, and dimension of the vector space. Fine. And let me just put this in somewhere. It's not cool. Let's start. So in the last two lectures, we saw what are vectors, right? So this 1 and 2 is a vector, 2, 3 is a vector, and they both are coming from R2, right? 1, 2, 3, 2, 3, 4, 3, 4, 6. All these are vectors and they're coming from R3, is what we had assumed, or what I had told you, that they're coming from the R3. Fine. Then we also saw that we can take the linear combination of these vectors. So what I can do is I can add these vectors, right? And I can get a new vector, 3, 5, right? I can also add these three vectors and I'll get a new vector. Fine. So I also can take the linear combination of these vectors. And we also saw that where the where these vectors used to lie, like the linear combination of these vectors used to lie. So when I was taking a linear combination of this plus b to 3, we saw that the linear combination belongs to R2, right? It can be any vector in the R2. Similarly, these three vectors, if I tell you that they are linearly independent, can you tell me where the linear combination will lie for these three vectors? You can comment on the chat. R3, right? So linear combination will lie in R3. Fine. But is this going to be the case always? So basically, uh, the linear combination is coming from where the vectors are being taken. So these vectors were taken from R2. So the linear combinations are lying in R2. These vectors were taken from R3, which is a set of 3D vectors, and the linear combination was lying in the R3 itself, right? Now what happens if I say that no, I'm not going to take the vectors from R2. I will actually define a set called S1, right? And here I will take all the multiples of this particular vector, which is 1, 2, which is a 2-coordinate vector. And also I'm going to take all the multiples of 2, 3. And I will create a set of this, right? So if I take the linear combination of these vectors or any of these two vectors, so if I do something like A of 1, 2 plus B of 2, 3, will it still lie in S1? In containing any two of them. Okay, so I will come here because Rohan said that plane containing any two of them. Is this a linear combination? So I'm telling you that these three are actually independent vectors, completely independent vectors, linearly independent. So this is a linearly independent set. Will they still lie in plane?
If we assume they are linearly independent, then it might not happen. But the A plus C equal to 2B, na? Here. First and the last the sum.
A plus.
AB series is.
Can you say that a little louder?
Yes, ma'am. Maybe I have some problem in microphone.
Sorry?
Am I audible now, ma'am?
Yeah, you are audible. Perfectly audible. Tell
The
me.
sum of the first and the last vector gives twice the middle vector.
Oh, is it? 4, 6.
Oh no, sorry. The last. Sorry, my bad.
No. So they are linearly independent. Okay, so we can visualize this also because this confusion came up. Let me just show these vectors. So this is vector 1, vector 2, and vector 3, right? So if I visualize them, they are actually in 3 different directions. Right? You can see that they're pointing in 3 different directions. So, and also the vector is not in the plane of any of the vector. Like the plane is not same. If third vector was lying in the was a linear combination of these two, it should have been here. It should have lied in the plane of this. From here you can see, right? These are 3 different vectors, 3 independent vectors. Clear, right?
Yes, ma'am. Yeah.
Fine. Cool. No problem. Fine. So they are linearly independent. I already told you they were linearly independent. So their linear combinations will lie in R3. Fine. Now let me come back to this. Yeah. So my question is that I say that I'm not taking 1 and 2, this vector and this vector from R2. I have defined a new set of vectors and I'm taking these vectors, and this is the set of vectors, and I'm taking 1 and 2 from here, right? So if I take any linear combination, any linear combination, will it still lie in S1? Let's say I want to do 3 and 5, right? Suppose I just added 1 into plus 2 and 3, right? It gave me this. Can anybody tell me that 3 and 5 is lying in this set S1 or not? No, right? Not lying in the S1, right? So basically, this is not lying in the S1. So here we see that it's not lying in the S1, right? What if I add 3, 5, multiples of 3, 5 now into my this set, right? Will now any linear combination of 1, 2 and 2, 3 lie in S2? Suppose I do 2 times 1, 2 plus 2 and 3. 2 and 3. And this is 2 plus 2, 4. 4 plus 3, 7. 4, 7. Right? Is 4, 7 lying in the same set, S2? Still not lying here, right? Still no. So, no. So it does not belong to S2. And here also, we saw that this does not belong to S1. Right? Now, what? Suppose I say that, okay, I will add all the linear combinations of 1 and 2 this set. Now, will the linear combinations of 1 and 2 and 2 and 3 belong to S3? Of 1, 2, 3, 2, S3. So everybody is saying right? Now it will belong, right? So it is belongs to S3, right? So what is so special about these set of vectors, right? So there is something special, right? So I cannot just have any set of vectors and take the linear and take 2 vectors from that and take a linear combination, and there is a guarantee that that linear combination will belong into that particular set from where I took the vectors, right? So when I took the vectors from this particular set, it was not guaranteed that when I take the linear combination of 1, 2, 2, 3, it belongs to the set. Similarly, when I defined the set S1, there was no guarantee that when I take any linear combination of these 2 vectors, it belongs to this set S1. So these sets, right? The set where you take the linear combination, where you take the linear combination of any vector and it still belongs to the set from which you have taken the original vectors. That particular set of vectors is called a vector space. Okay, so special name for those vectors is vector space. And we have been seeing these vector spaces all along, right? I explicitly did not mention it to you guys but when I said that this is coming from R2, this is coming from R3, this is coming from R, they are actually vector spaces. Okay. Now let me formally define vector spaces for you. Okay. So vector space V is a set of vectors which follow certain properties. So let me just do this. Okay. So a vector is a set of vectors which will follow these 10 properties. So if I have to number them, there are some 10 properties. 9, 10. Fine. Let's talk about these properties one by one. Fine. So let's first look at these set of properties. So this property is basically telling me if I take two vectors, x and y, which belong to V. Actually, I take three vectors. I will take only two vectors for now. If it's saying that if I take two vectors which belong to V, x plus y is equals to y plus x. Fine. So this is called the uh, commutative property of addition, right? Commutative property of addition. Commutative, yeah, no, this is called commutative property of addition. Fine. Now so what I'm saying is that if I add vector x or y, or like x plus y, or if I do y plus x, they should be same. Fine. And we know that in R2 or R3, this property holds, right? So first property is the commutative property of addition. Now let's come to the second property. So they're saying that if z also belongs to V, so there is a third vector that belongs to V. So if I add x plus y plus z, then it should be equal to x plus y plus z. So it should not matter which two vectors I'm adding first. So I can add y and z first as well, or I can add x or y first as well. But the sum of three vectors should be equal, right? So this is called associative property of addition. Fine. Now the third property, it says that x plus 0 is equals to x. Fine. It also says one more thing. It says that there should be a vector or element 0 such that when I do x plus 0, I should get back x. Additive identity, correct. So this is called additive identity. Right? And it should hold for all the vectors that I have in my set V. Also, the fourth property is if I add the negative of a vector, okay? So it's called additive inverse. Then I should get back the 0 vector. So this is called additive inverse. Okay. And these properties, which I have here, they are called additive properties of a vector space. So I just erase this. These are additive properties of vector space. Additive properties. So we can check, right? So suppose I take R2. So if I add any vector, any two vector, and I reverse the order in which I add, this will still hold, right? If I take three vectors from R2 and no matter what order I add them in, I will always get the same vector. Similarly, in R2, there is always a 0 vector to which when I add the vector that I've taken from the vector space, it gives me back the vector. For example, if I take 2, 0 and I add 0, 0, it gives me back 0, 0, 2, 0, right? Similarly, also in my vector space R2, I have seen that when I have a vector 2, 2, and when I add the negative of this vector is -2, -2, I always get the 0 vector, right? So these properties are satisfied in standard vector spaces R, R2, R1, R2, R3, and Rn. Fine. Let's move to another four properties. So these properties are called multiplicative properties of a vector space. Multiplicative properties of a vector space. Fine. So for any x and y that belongs to E. And C1, C and C2 belongs to R. Fine. So what it is saying is that I should have a vector 1 egg such in the vector space such that when I multiply, sorry, actually not that. Just let me correct this. Yeah. What it's saying is if I multiply a vector with 1, okay, then I should get back the vector itself. Fine. So this is called multiplicative identity. Okay. Identity. Another property is, so these properties are very similar in additive and multiplicative properties. Other properties that I have C1, C2, X. So I have two constants which I have taken from the real number or the scalars. And no matter in what order I multiply them, it should give me the same value, right? So what is this property called? Anyone can answer? Associative property, right? So this is associative property of multiplication. Another property is that if I have a constant and I'm multiplying it to a sum of two vectors, then I can also write it as I individually multiply those vectors with a scalar and I add them. So this is a distributive property. There is another distributive property where it says that if I have some sum of two scalars and I multiply it to the vector, I can individually multiply the scalar to the vector and add them, and it should give me the same value. So this is also the distributive property of multiplication, right? So all these eight properties that we have talked about, right? They are somewhat implicit. Like we always assume them. We don't always try to assure, like we will assume in the linear algebra that we'll study so far that these always hold. Fine. The next properties that I'm going to talk about is something which is important. So these properties are called closure properties. Closure properties. Okay. So for X and Y that belong to V, it's saying that if I take a linear combination, if I do C1X plus C2Y, then it also should belong to V, right? And this was a property that was not being satisfied in the sets S1 and S2, right? Not satisfied. I didn't. S1 and S2 sets, correct? Also, they say that if I have a vector X that is coming from the vector space V, all the multiples of it should also belong to V. Fine. So if I define a set, say S star, and I say I have just one of this vector, will this be, or I will say, yeah, will this be a vector space? Is this a vector space? Let me know on the chat box. No, right? No, it will not be. So, first of all, the basic thing that is missing is multiplicatives are not there, right? So I don't have C of 1 does not belong to V, right? So this is not a vector space. But what if I add C of Now I am defining another set. Okay. So first condition is actually sufficient, but it's defined for two vectors. Okay. And suppose there is just one vector. For example, in this example, which I'm going to give you, suppose this is how I define my vector, right? And C belongs to R, right? Is H double star a vector space? Correct, right? So the reason that we define these two properties, you're right that this is somewhat captures the whole essence of closure. This is just for the vectors which are, singular in the vector space. For example, this particular vector space, it has just a single vector and all its multiples, right? So is this a vector? Yeah, we can do C2 is 0, but there is no other vector, right? There is no there is no y in this S double star. Doesn't make sense? Like there is no two different vectors belonging to S double star. There is just one vector which belongs to S double star. Make sense?
Ma'am, am I audible?
Yeah, you're audible. A little voice is breaking, but yeah, go ahead.
Actually, I was asking in that example that you took, we have like the next slide.
Next slide, right? Yeah.
E to 1 to this vector. So here we have many vectors now.
Right. We have many vectors actually.
Yeah. So if someone is mentioning the first property, then the second property so automatically follows from there.
It does. It does. I agree. It does. Actually, it does. It just they define it for two vectors, like the linear combination of two vectors. They do.
Okay.
Yeah, it does. It actually includes this. You can just take C2, 0, 0 and Y as the same vector. It does that, but there is just for the sake of completion, I think these two properties are given differently. Right? So is this a vector space? And you guys said yes, right? Because additive properties and multiplicative properties will assume that it always holds. We can see that C of like any multiple of 1 and 2 will belong to this set. Fine. Fine. So are R1, R2, Rn vector spaces? I kind of mentioned this in the slides already, but they are, right? Yes, they are. Because of the same reasons that they follow the additive properties, they follow the closure properties, and they also follow the multiplicative properties. So this is correct. They're actually called standard. There's another name, standard vector spaces. Okay. Fine. Okay. Now tell me, is this a vector space? We actually already saw it, but let's see it again in terms of vector space. You didn't know the vector space. Right? So this is not a vector space because if I do 1, 2 plus 2, 3, which is equals to 3, 5, that does not belong to S1. Right? So not a vector space. What about this? So if I do 1, 2, 2 plus 2, 3, which is 4, 7, it will never belong to the vector space S2. So no. Fine. What about this one? Fine. So this is yes, this is indeed R2. Rohan, you're right that this is indeed R2. Yes, but this is a vector space. Last slide. Okay, let me go back here. This one?
Yes, ma'am. Yes.
Yeah.
Ma'am, this one, isn't it vector space?
No. So I gave you an example, right? So there are two closure properties. Fine. One is that multiplicatives of the individual vector should exist. Also, the linear combination of the vectors should exist. So if I take this linear combination where I just add 1, 2, 1, 2, 3, I will not get 3, 5, right? Can you confirm that?
Ma'am, we are getting 3, 5 actually.
How will we get?
If we add 1, 2 and 3, 2.
No. So, okay. So what is this vector space? Okay, let me expand this set. Okay, so it has multiples of 1, 2. Okay, so it has 1, 2, it has 2, 4, blah, 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 say 100, 200, fine. And it also has 2, 3, and also the negatives of it. 4, 6, blah, 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 200, 300, and so on.
Ma'am, can I just interrupt once?
Yeah, sure.
Actually, Rohan has said that I mistook it as a span of those two vectors. So yes, I am thinking that span of these two vectors will be a vector space. So was that the only question?
No, I'm asking, is this a vector space? I have defined the set. I have defined a set to be the set of these vectors. Okay, so this set just contains these vectors. I'm not talking about span anywhere.
Okay.
Or maybe this curly brace notations, as somebody saying, confused you. But whenever I say span, I will always say span of curly brace, whatever vectors I have. Okay. Okay.
Ma'am, but actually span only forms a space, right?
Yes, I'll come to that next.
So my question is that without asking about the span, can we comment on any problem that whether it is a space or not?
We can, right? So I told you the properties of a vector space. I told you that it should have the additive properties, the multiplicative properties, and the closure properties, right? Then I am showing you a set which has all these vectors.
Okay. Yeah, got it.
Right?
Somewhat
I am saying that all these vectors are there. Now tell me, is this a vector space? And vector space is nothing but a set of vectors, right? So I can talk about any set of vectors and ask you whether it's a vector space or not. Right? Makes sense now? If you have any confusion, we can clear it now. No issue.
No, ma'am. When you have used a set of vectors word, now I got it.
Okay. Did I not use it before? I think I was.
No, ma'am, actually.
Okay. Let me see. Oh, I must have mentioned it. I should have explicitly mentioned that this is a set. Set of vectors. Okay. Anybody has a similar confusion that this was a set and not span? Fine. Okay. That I should have emphasized more on the word set. Anyways, thank you for clearing that out. Okay, let's move on. Okay, so this is a vector space, fine. We saw that, okay, all the linear combinations of these two vectors and also the multiplicators of these two vectors are in the set S3. So S3 is a vector space. Fine. Cool. Now another question. Is S3... okay. Okay, let me first define another terminology. Okay. So this is actually some set, right? This is some set. Even this is some set. And even this is some set, right? So sets also have something called a subset, right? Subset. Subset is nothing but can have less or equal number of elements. Of a set, right? So if I have a set, say 1, 2, 3, subset S1 can have 1 and 2. And I will say that S1 is a subset of S. Is this clear to everyone? Everybody knows what is a subset and a set is, right? So tell me the question now, that is S3 a subspace of R2?